the equilibrium constant of a chemical reaction is the value of the reaction quotient when the reaction has reached equilibrium. At any given temperature, the equilibrium constant has a value which is independent of the initial and actual concentrations of the reactant and product species. For a given set of initial concentrations, the equilibrium constant can be used to determine the composition of a system at equilibrium. For a general chemical equilibrium, the thermodynamic equilibrium constant can be defined such that, at equilibrium, where curly brackets denote the thermodynamic activities of the chemical species, the right-hand side of this equation corresponds to the reaction quotient Q for arbitrary values of the activities, and becomes the equilibrium constant as shown when the reaction is at equilibrium. The logarithm of this expression appears in the formula for the Gibbs free energy change for the reaction. If deviations from ideal behavior are neglected, the activities of solutes may be replaced by concentrations, A, and the activity quotient becomes a concentration quotient, Kc. Kc is defined as equal to the thermodynamic equilibrium constant but with concentrations of reactants and products instead of activity coefficients. Again, assuming ideal behavior, the activity of a solvent may be replaced by its mole fraction, or approximately by 1 in dilute solution. The activity of a pure liquid or solid phase is exactly 1. The activity of a species in an ideal gas phase may be replaced by its partial pressure. A knowledge of equilibrium constants is essential for the understanding of many chemical systems, as well as biochemical processes such as oxygen transport by hemoglobin in blood and acid-base homeostasis in the human body. Stability constants, formation constants, binding constants, association constants and dissociation constants are all types of equilibrium constant. See also determination of equilibrium constants for experimental and computational methods. Types of equilibrium constants, cumulative and stepwise formation constants. A cumulative or overall constant, given the symbol I², is the constant for the formation of a complex from reagents. For example, the cumulative constant for the formation of Ml2 is given by the stepwise constant, K, for the formation of the same complex from Ml and L is given by. It follows that a cumulative constant can always be expressed as the product of stepwise constants. There is no agreed notation for stepwise constants, though a symbol such as KLML is sometimes found in the literature. It is best always to define each stability constant by reference to an equilibrium expression. Competition method. A particular use of a stepwise constant is in the determination of stability constant values outside the normal range for a given method. For example, EDTA complexes of many metals are outside the range for the potentiometric method. The stability constants for those complexes were determined by competition with a weaker ligand. The formation constant of Pd, Cn, 4,2 was determined by the competition method. Association and dissociation constants. In organic chemistry and biochemistry it is customary to use pKa values for acid dissociation equilibria, where Kdiss is a stepwise acid dissociation constant. For bases, the base association constant, pKb is used. For any given acid or base the two constants are related by pKa plus pKb equals pKw, so pKa can always be used in calculations. On the other hand, stability constants for metal complexes, and binding constants for host-guest complexes are generally expressed as association constants. When considering equilibria such as, it is customary to use association constants for both Ml and HL. Also, in generalized computer programs dealing with equilibrium constants it is general practice to use cumulative constants rather than stepwise constants and to omit ionic charges from equilibrium expressions. For example, if NTA, nitrilacetic acid, NCH2CO2H, 3 is designated as H3L and forms complexes Ml and MHL with a metal ion M, the following expressions would apply for the dissociation constants. The cumulative association constants can be expressed as. Note how the subscripts define the stoichiometry of the equilibrium product. Microconstants. When two or more sites in an asymmetrical molecule may be involved in an equilibrium reaction, there are more than one possible equilibrium constants. For example, the molecule L-DOPA has two non-equivalent hydroxyl groups which may be deprotonated. Denoting L-DOPA as LH2, the following diagram shows all the species that may be formed Co2H. The first protonation constants are L1H equals K11, L-H, L2H equals K12, L-H. The concentration of LH is the sum of the concentrations of the two microspecies. Therefore, the equilibrium constant for the reaction, the macro constant, is the sum of the microconstants. K1 equals K11 plus K12. In the same way, K2 equals K21 plus K22. Lastly, the cumulative constant is I squared 2 equals K1 K2 equals K11 K21 equals K12 K22. Thus, although there are 6 micro and macro constants, only 3 of them are mutually independent. Moreover, the isomerization constant, K, is equal to the ratio of the microconstants. K equals K11 per 12. In L-DOPA the isomerization constant is 0.9, so the microspecies L1H and L2H have almost equal concentrations at all pH values. In general, a macro constant is equal to the sum of all the microconstants, and the occupancy of each site is proportional to the microconstant. The site of protonation can be very important, for example, for biological activity. Microconstants cannot be determined individually by the usual methods, which give macroconstants. Methods which have been used to determine microconstants include blocking one of the sites, for example by methylation of a hydroxyl group, to determine one of the microconstants, using a spectroscopic technique, such as infrared spectroscopy, where the different microspecies give different signals. Applying mathematical procedures to 13 CNM data. pH considerations. pH is defined in terms of the activity of the hydrogen ion. In the approximation of ideal behavior, activity is replaced by concentration. pH is measured by means of a glass electrode. A mixed equilibrium constant, also known as a Bryan-Sted constant, may result. It all depends on whether the electrode is calibrated by reference to solutions of known activity or known concentration. In the latter case, the equilibrium constant would be a concentration quotient. If the electrode is calibrated in terms of known hydrogen ion concentrations, it would be better to write pH rather than pH, but this suggestion is not generally adopted. Hydrolysis constants. In aqueous solution, the concentration of the hydroxide ion is related to the concentration of the hydrogen ion by. The first step in metal ion hydrolysis can be expressed in two different ways. It follows that I squared equals K/Kw. Hydrolysis constants are usually reported in the I squared form, and this leads to them appearing to have strange values. For example, if Lgk equals 4 and Lgkw equals a 14, Lgi squared equals 4 plus equals a 10. In general, when the hydrolysis product contains N hydroxide groups, Lgi squared equals Lgk plus N Lgkw. Conditional constants. Conditional constants, also known as apparent constants, are concentration quotients which are not true equilibrium constants but can be derived from them. A very common instance is where pH is fixed at a particular value. For example, in the case of iron, 3, interacting with EDTA, a conditional constant could be defined by. This conditional constant will vary with pH. It has a maximum at a certain pH. That is the pH where the ligand sequesters the metal most effectively. In biochemistry, equilibrium constants are often measured at a pH fixed by means of a buffer solution. Such constants are, by definition, conditional, and different values may be obtained when using different buffers. Gas phase equilibria. For equilibria in a gas phase, fugacity, F, is used in place of activity. However, fugacity has the dimension of pressure, so it must be divided by a standard pressure, usually 1 bar, in order to produce a dimensionless quantity, F/P. An equilibrium constant is expressed in terms of the dimensionless quantity. For example, for the equilibrium 2NO2N2O4. Fugacity is related to partial pressure, P, by a dimensionless fugacity coefficient I, F equals IA euro P. Thus, for the example, usually the standard pressure is omitted from such expressions. Expressions for equilibrium constants in the gas phase then resemble the expression for solution equilibria with fugacity coefficient in place of activity coefficient and partial pressure in place of concentration. Thermodynamics, definitions, for a general chemical equilibrium. The thermodynamic definition of the equilibrium constant is that, at equilibrium, where A is the activity, at equilibrium, of the chemical species A, etc. It is conventional to put the activities of the products in the numerator and those of the reactants in the denominator. Since activity is a dimensionless quantity, the thermodynamic equilibrium constant, K, is also a dimensionless quantity. This is important because K is related to the standard free energy change, Ig, for the reaction. R is the gas constant and T the absolute or thermodynamic temperature. Taking the logarithm of K is only possible when K has no dimensions, that is, when it is a pure number. However, it is often more convenient to use concentrations than activities, so the equilibrium expression may be written as the product of three components: a reaction quotient of equilibrium concentrations, QE, a quotient of activity factors, I, and a quotient of standard concentrations, CO. The symbol, A, stands for a generalized concentration or partial pressure of the chemical species A. The activity coefficients, I cubed, are dimensionless, and Ca stands for the standard concentration or standard partial pressure. By convention, the standard concentrations have a value of 1 mol per decimeter 3, so the third factor, CO, has a numerical value of 1 and units that are the reciprocal of the units of the concentration quotient. K remains dimensionless, so the expression simplifies to. It follows that the concentration constant, Kc, is related to the thermodynamic equilibrium constant by. Note that when Kc is defined in this way it has no dimension, so log Kc is permissible. When an equilibrium constant value is to be determined, there are three options for dealing with the activity coefficients. Use known or calculated activity coefficients, together with concentrations of reactants. For equilibria in solution, estimates of the activity coefficients of charged species can be obtained using de Broglie 1/4 CKEL theory, an extended version, or SIT theory. For uncharged species, the activity coefficient I cubed 0 mostly follows a salting out model, log 10, I cubed 0, equals bar I, where I stands for ionic strength. Assume that the activity coefficients are all equal to 1. This is acceptable when all species are uncharged and the solvent has low polarity. For equilibria in solution, use a medium of high ionic strength. In effect, this redefines the standard state as referring to the medium. Activity coefficients in the standard state are, by definition, equal to 1. The value of an equilibrium constant determined in this manner is dependent on the ionic strength. When published constants refer to an ionic strength other than the one required for a particular application, they may be adjusted by means of specific ion theory and other theories. Units: Kc appears to have the dimension of concentration to the power Z, the difference of the sums of the powers in the numerator and denominator, Z equals I plus I florin plus A. It must in fact be dimensionless or it would not be possible to take its logarithm. The illusion is the result of omitting the standard concentrations from the defining expression. Nevertheless, it is not unusual, particularly in texts relating to biochemical equilibria, to see a value quoted with the dimension. Some examples are as follows. Where the symbol M signifies a molar concentration. In writing these expressions, there is an implicit assumption that the quotient of activity coefficients is equal to 1. Furthermore, the subscript C is often omitted, implying that the concentration quotient is a thermodynamic equilibrium constant, in the sense defined above. In these cases, the unit in effect specifies the concentration scale to which the concentrations, A, B, etc. refer. Implicitly, the standard concentrations are on that scale too. In speciation calculations one must define the equilibrium constant as a quotient of concentrations, K equals QE. Then, the equilibrium constant has dimensions, such as mR1 or mR1, a unit sometimes used in biochemistry. For example, for the formation of an adduct A plus BAB the concentrations, A, and B, can be calculated by solving the equations of mass balance. Where TA and TB are the analytical concentrations of the reagents A and B and the numerical value of K is known, each term in the expressions should have the same unit of concentration so that the numerical values of the concentrations can be calculated. In this example, assuming molar concentrations, the product concentration, AB equals K, A, B, has dimension mR1 M equals M, the same as a TA, TB, A, and B. Derivation of equilibrium constant expression, temperature, T, is assumed to be constant in the following treatment. Thermodynamic equilibrium is characterized by the free energy for the whole system being a minimum. For systems at constant pressure the Gibbs free energy is minimum. The slope of the reaction free energy, IgR with respect to the reaction coordinate, I3/4, is 0 when the free energy is at its minimum value. The free energy change, IgR, can be expressed as a weighted sum of chemical potentials, the partial molar free energies of the species in equilibrium. The potential, I1/4I, of the ith species in a chemical reaction is the partial derivative of the free energy with respect to the number of moles of that species, Ni. A general chemical equilibrium can be written as Nj are the stoichiometric coefficients of the reactants in the equilibrium equation, and Mj are the coefficients of the products. The value of IgR for these reactions is a function of the chemical potentials of all the species. The chemical potential, I1/4I, of the ith species can be calculated in terms of its activity, I. I1/4I is the standard chemical potential of the species, R is the gas constant and T is the temperature. Setting the sum for the reactants J to be equal to the sum for the products, K, so that IgR, Ek, equals 0. Rearranging the terms. This relates the standard Gibbs free energy change, Ig, to an equilibrium constant, K, the reaction quotient of activity values at equilibrium. Temperature dependence, the Van 't Hoff equation, shows that when the reaction is exothermic, then K decreases with increasing temperature, in accordance with Le Chatelier's principle. It permits calculation of the reaction equilibrium constant at temperature T2 if the reaction constant at T1 is known and the standard reaction enthalpy can be assumed to be independent of temperature even though each standard enthalpy change is defined at a different temperature. However, this assumption is valid only for small temperature differences T2 or T1. In fact, standard thermodynamic arguments can be used to show that where Cp is the heat capacity at constant pressure, the equilibrium constant is related to the standard Gibbs energy change of reaction as where Ig is the standard Gibbs free energy change of reaction, R is the gas constant, and T the absolute temperature. If the equilibrium constant has been determined and the standard reaction enthalpy has also been determined, by calorimetry, for example, this equation allows the standard entropy change for the reaction to be derived. A more complex formulation, the calculation of K at a particular temperature from a known K at another given temperature can be approached as follows if standard thermodynamic properties are available. The effect of temperature on equilibrium constant is equivalent to the effect of temperature on Gibbs energy because where Ig is the reaction standard Gibbs energy, which is the sum of the standard Gibbs energies of the reaction products minus the sum of standard Gibbs energies of reactants. Here, the term standard denotes the ideal behavior and a hypothetical standard concentration. It does not imply any particular temperature or pressure because, although contrary to IUPAC recommendation, it is more convenient when describing aqueous systems over wide temperature and pressure ranges. The standard Gibbs energy can be represented as in the above equation, the effect of temperature on Gibbs energy is ascribed entirely to heat capacity. To evaluate the integrals in this equation, the form of the dependence of heat capacity on temperature needs to be known. Now, if one expresses the standard heat capacity Cp, as a function of absolute temperature using correlations of the following forms, for pure substances. For ionic species at T less than 200 deg C. Then the integrals can be evaluated and the following final form is obtained. The constants A, B, C, A, B and the absolute entropy, 298, required for evaluation of Cp, T, as well as the values of G298K and S298K for many species are tabularized in the literature. Pressure dependence. The pressure dependence of the equilibrium constant is usually weak in the range of pressures normally encountered in industry, and therefore, it is usually neglected in practice. This is true for condensed reactant products as well as gaseous ones. For a gaseous reaction example, one may consider the well-studied reaction of hydrogen with nitrogen to produce ammonia, N2 plus 3 hours 22NH3. If the pressure is increased by an addition of an inert gas, then neither the composition at equilibrium nor the equilibrium constant are appreciably affected. However, the composition at equilibrium will depend appreciably on pressure when the pressure is changed by compression of the gaseous reacting system, and the reaction results in the change of the number of moles of gas in the system. In the example reaction above, the number of moles changes from 4 to 2, and an increase of pressure by system compression will result in appreciably more ammonia in the equilibrium mixture. In the general case of a gaseous reaction, the change of mixture composition with pressure can be quantified using where P denote the partial pressures of the components, P is the total system pressure, X denote the mole fraction, Kp is the equilibrium constant expressed in terms of partial pressures and Kx is the equilibrium constant expressed in terms of mole fractions. The above change in composition is in accordance with Le Chatelier's principle and does not involve any change of the equilibrium constant with the total system pressure. Indeed, for ideal gas reactions Kp is independent of pressure. In a condensed phase, the pressure dependence of the equilibrium constant is associated with the reaction molar volume. For reaction, the reaction molar volume is where V denotes a partial molar volume of a reactant or a product. For the above reaction, one can expect the change of the reaction equilibrium constant with pressure at constant temperature to be. The matter is complicated as partial molar volume is itself dependent on pressure. Data sources: IUPAC-SC database, a comprehensive database of published data on equilibrium constants of metal complexes and ligands. NIST Standard Reference Database 46 critically selected stability constants of metal complexes, inorganic and organic acids and bases pKa data in water and DMSO. NASA Glenn Thermodynamic Database webpage with links to temperature-dependent specific heat, enthalpy, and entropy for elements and molecules. See also, determination of equilibrium constants, stability constants of complexes, equilibrium fractionation, external links, Science Aid, equilibrium constants explanation of Kc and Kp for high school level, references.